The name of this video is Magnetic Materials. A Bohr magneton. This is our first video on a long series of videos about magnetic materials. We will follow a similar analysis for what we have done for dielectric materials. And so it's worth already now to start to make a comparison between insulating materials here on the left versus magnetic materials here on the right. So in insulating materials, the typical insulating material we encountered in this course are dielectric materials. In fact, dielectric materials are the most important insulating materials. There are also other materials such as ferroelectric materials, but there are not so many. So it's very important for research, but for an introduction to electromagnetism, electric materials is where you want to start. And so we know that in this case, the key item is that the key idea behind the electric materials is that they are made up of an ensemble of molecules where each molecule is effectively an electric dipole with a negative charge and a positive charge, which are connected by means of the vector displacement vector L, which is the amount the molecule stretches when it is placed in an external field E naught. So in this case, we know that the key equation is that P is equal QL. So the positive charge is Q, the dipole moment, the electric dipole moment P, is given by Q positive times L. So this we have seen it extensively. Similarly, for magnetic materials, actually to some extent, all materials are magnetic, to some extent. So to some extent, all materials are magnetic materials because basically every material is made of atoms, and these atoms, for example, we can represent an atom. Let's suppose that we consider an atom with some protons and electrons moving around in a very simplistic model of such an atom is basically the planetary model. And so we have the electrons moving around the protons. And so these electrons generate effectively a current around the protons. Okay. And so how do we show that? So in a simple fashion, we basically have a current I associated with these electrons which are moving around the protons, which are somewhere here in the center. There is an area associated with this simple planetary model of an atom inside any material. And so if we define as n, right-hand rule, so this is our vector n, normal to the area, and consistent with the right-hand rule with the direction of I1. And so this area here, we call it A. Well, then, the oriented area, of course, is NA. In this case, what is the dipole moment associated with this object? Okay, so if these are atoms, they are quasi-ideal dipoles, and the dipole moment of a quasi-ideal dipole, we call it, typically dipole moment, we call it small m. Let's call it directly mu, as we've seen a few videos ago. So mu in this case, which is the dipole moment of these quasi-ideal dipoles, electrons moving around protons, mu vector, this is also a vector, is obviously given by the current, as we have seen for quasi-ideal dipoles, times NA, the oriented surface. Okay, so this is the key that we are going to use to understand magnetic materials. Okay, so each atom is like a little loop of current. which is quasi-ideal with a moment mu. Great. So as it turns out, as I just said, in the case of insulating materials, the most important one are dielectric materials, whereas ferroelectric materials are less, we are not going to talk about them, so let me put it in parentheses. They're important for research, but they're less, it's actually more complicated and less relevant for this course. Whereas in the case of magnetic materials, as it turns out, the key ones are ferromagnetic materials. So while we didn't discuss about ferroelectric materials, we will discuss quite a bit about ferromagnetic materials. And so ferromagnetic materials are highly nonlinear, which is quite important. We'll come back to the classification of materials later on. So they are highly nonlinear. An example of such materials, for example, we have iron, Fe, nickel, Ni, cobalt, and basically any iron oxide which creates magnets, like the magnets, of course, that you have on your fridge. Okay, we'll come back to these magnets. We will study magnets later on in a few videos from now. So these are some critical examples. As it turns out, in the case of magnetic materials, diamagnetic, we will also study diamagnetic and paramagnetic materials, / paramagnetic. However, these materials, both diamagnetic and paramagnetic materials, are approximately like vacuum. Okay, so we need to distinguish them from vacuum, but for many applications, they're basically like vacuum. And so if you take a piece of copper and you put it in an external B field, for us, experimentalists, it's basically like vacuum. So unless you're really studying the properties in detail of these materials, in many experiments, we can basically treat them as vacuum. Whereas ferromagnetic materials, you definitely cannot. And in fact, one of the features that it's important of ferromagnetic materials, as soon as you have a solenoid with a ferromagnetic material like the core of the solenoid, all the equations we use for self-mutual inductances fail because they are valid for linear materials, whereas these are highly nonlinear. So a typical way to solve that problem is to linearize the characteristic of this, the constitutive relation of these materials, as we shall see. Linearization means if it's very complicated, non-linear curve, we just set ourselves in we bias ourselves in a special point, and we only work around the point where we can linearize this complicated curve, and we'll come back to that. All right. So this is a general introduction to insulating versus magnetic materials, which now is the topic of the next video, magnetic materials. And so to further discuss about magnetic materials in this qualitative fashion, is worth introducing the Bohr, Rutherford model of the atom, of the hydrogen atom, from 1913, the version from 1913, let's say, which of course does not take into account in detail of all the quantum mechanical effects for the hydrogen atom, but is actually a very good model to understand magnetic materials. And actually still pretty accurate, as it turns out. So how does it work? So we have the hydrogen atom, so there is a single proton, positive here, with a single electron moving around in this planetary model, where the distance between the proton and the electron, let's call it vector r, and let's call it vector rn, okay, subscript n in general. And so this electron moves around in an orbit around the proton in this fashion, okay? And there is an area A associated with this orbit, let's say AN, which depends on the radius we are considering n. So if this one is a stationary orbit, this implies that Rn is quantized. That's actually what also the model tells us. So there is some quantization here happening. So it's discrete. You can only have a discrete set of Rn's, okay? R1, R2, etc. And I also remind you that the angular frequency, in this case, omega, is defined by 2 pi f. We're going to use it later. What is this frequency? Is the rate at which the electron moves around this proton. So there is a period associated with this motion, the inverse of which is f, and if I multiply times 2 pi, I obtain the angular frequency, whereas f is the frequency in radiant. Now, if it so happens that we choose the first orbit and the lowest one in this quantization, n equal 1, well then we obtain R1, which is the so-called Bohr radius, and the Bohr radius is approximately equal to, to be more specific, is approximately equal to 5.29 times 10 to the minus 11 meter. 5.29 times 10 to the minus 11 meters. That's the Bohr radius. Okay, so let's write it here. So this is our Bohr radius, which is again associated with the lowest orbit of this set of quantized orbits. Now, how do we write in this case mu, which we call it actually mu b for Bohr, okay, which is of course a vector, and I will just write down now, because this is an oriented curve like here, but let's only look at the magnitude of this mu b, which is the magnetic dipole moment associated with this simple model, the Bohr-Rutherford model of the hydrogen atom. Well, it's equal to the current I times the area A. What is the current I? So the current is the charge per unit time. So it has to be the only charge we have available here, which is the electron charge, moving around this proton in a period capital T, times the area, which is pi. Let's choose A1, so it's R1 square, the lowest orbit. Okay, so this we can rewrite it as E times the inverse of T is F. The inverse of T is F, so we can do EF, but F is omega over 2 pi. Okay, so we exchange T with omega over 2 pi times pi R1 square, so this pi goes away. Therefore, obtaining a new expression which I can multiply by the mass of the electron and divided by the mass of the electron, for example. If I do so, multiply and divide by the mass of the electron, and then I have E omega half times R1 square. Okay, so how can we rewrite this expression for mu b? This we can rewrite it as, let's put together me omega and R1 square. So we can rewrite it as parentheses, the mass of the electron times omega, the angular frequency, times R1 square, the Bohr radius square of the lowest orbit in this quantized set of orbits, times E over 2 times me. The electron charge times 2 times the mass of the electron. Okay. Now, what is this quantity in parentheses? Well, actually, this quantity in parentheses is nothing but h bar, the normalized Planck constant, times E divided by 2 times me. And what we wrote here, so this quantity here, is called the Bohr magneton, as the title says here of this video. So this quantity is the Bohr magneton. Very important. I remind you that n h bar is equal to me more in general for any other orbit, omega Rn quantity square, but this is another orbit if you want. And so, so now that we have the Bohr magneton, why is me omega R1 square equal h bar? Well, actually, that's a question which I leave for you on Piazza. So what I would like you to do is to show what is h bar, the relationship between h bar and this me omega R1 square. And what you need to know is the quantization of energy. So the energy is quantized as h bar omega, or hf if you want, similarly. And you also need the energy due to the centripetal force in this case. to the centrifugal force for, let's say, 1 radiant. And so if you do this and you combine these two aspects, you should be able to show to me that h bar is me omega r1 square, okay? So to recap this video, this is a very qualitative introduction to magnetic materials using the concept of Bohr magneton. So insulating materials, the most important ones, dielectric materials, we didn't study and we will not study ferroelectric materials. In this case, the electric dipole moment small p is q, the positive charge, times the distance, which is whatever it stretches between in the molecules after placing it in an external field. Magnetic materials, to some extent, all materials are magnetic because they are made of atoms where we have electrons moving around the proton, giving rise to a current I, and here we assume that this current is stationary. And so the area A of this loop, of course, gives a mu, which is I and A. And the most important magnetic materials, however, are highly nonlinear. They are ferromagnetic materials like iron, nickel, cobalt, and magnets, those that you put in the fridge. We will also touch a little bit about diamagnetic and paramagnetic materials, which are similar to vacuum, and they behave linearly, whereas ferromagnetic are nonlinear. So how to understand a little bit more in detail what's happening here with this, why all materials to some extent are magnetic? Well, let's look at even the simplest hydrogen atom, and we look at the Bohr-Rutherford model from 1913, a proton and an electron, moving in a stationary orbit, which is quantized with Bohr radius R1. So mu, in this case, we call it mu B for Bohr, and it's IA1 without n because we're only looking at the magnitude. And so the current is the electron over the time. Remember that the current intensity is dq over dt. So it's q over t in this case. By manipulating a little bit, we were able to show that mu B is h bar E over 2 me, the Bohr magneton. That's it.